convolution, discrete Fourier transform, and how polynomials relate these to wonderful ideas in mathematics. And so, what is a convolution? Convolution is a process that we do on two signals, and we acquire another new signal from it. And this convolution process, it can be done both in temporal signals and also in spatial signals such as image. And this kind of convolution is something that has created the field of neural network using or we know as them convolutional neural network. And so this is a very impactful operation indeed. And what is discrete Fourier transform? Discrete Fourier transform is another powerful concept that we can see in the realm of computer science and also in signal processing, also in controls and systems. Very useful process indeed. And the idea that relates them to is very powerful. That the convolution of two signals will be the multiplication of their discrete Fourier transforms. And how we get to that idea are might be at first that might be very difficult to understand, but we will show with some simple algebraic expressions that okay, that convolution and discrete Fourier transform, they might not be that different at all. And this not only will extend to discrete Fourier transform but also other transformations such as Laplace transform or Z transforms if you know them, and even discrete cosine transform uh, that is a very unique algorithm that helps us in the modern computer vision field. So discrete Fourier transform, what this is? Discrete Fourier transform is a summation, what do you call a summation transformation. Also the discrete version of continuous integral transformation. Other than that, it just takes a signal and it just creates another signal, although this another signal will be in the complex domain. So that is to keep in mind. And uh, other than that, discrete Fourier transform isn't that much difficult to understand really. It just is a summation of a bunch of complex numbers. So for example, we have a signal here 1, 4, 8, and 1. This is a discrete one-dimensional signal, and we're defining x of k as the discrete Fourier transform of this signal. And if we run the numbers here, you can see it is a pretty simple formula, and this will correspond to 1. This will be this will be a complex number. This will be another complex number, and so on. So 1481 with a e to the power minus j for theta, where theta is this expression. So although it seems a little bit archaic, but what is actually is doing is just taking the roots around the unit circle in the complex number. Now this is something that will be that can be done in detail while learning about discrete Fourier transform, but this is not the scope of our lecture. Our lecture will go first to convolution. So convolution is another of those simple what do you call operations that are that is very impactful again. So one of the examples we have here that 132, this is a signal, and 121, this is another signal, and C is just a convolution B. This is the convolution symbol we have right here. So if we run this convolution, so we see that we take the signal, first one, and the second one, it is actually reversed, although you cannot see it because it's a symmetric signal, and most of the time in at least in image processing we'll see a symmetric signal, signal, yeah. And what you do is you shift one and you take the dot product of it and you get 1. So that is your first result, and again you shift one element to the side and you take the dot product, you get the next one, so on and so on. You get this new signal you have right over here. That is the convolution of these two signals. Now notice something interesting. The signals we have were 1, 3, 2 and 1 to 1. Let's define two polynomials that take the coefficients as those signals. So 1, 3, 2 here and 1 to 1 over here. This is just means and 1 over here. And if we multiply them, you see we get this new polynomial. And if you notice carefully, the coefficients we have right over here, they are nothing but the signal C, which is the convolution of A and B, which means multiplying two polynomials together is somehow the same as convoluting them. Now, this idea, if you exercise it a little bit more, you can see that x can be anything. Like, this is a geometric idea, right? So this idea is very much geometric, and we can say that x can be literally anything. X can be a number, x can be a matrix, and still this summation expression will hold. X can be a function like sine of x, for example, or sine of theta, to be exact. And the expression will still hold. So let's just say x to be a function, a very special function. Let's set x to be this monstrosity here. I say it's a monstrosity, but if you look at it, it's just the nth root of unity. Nth root of unity, which means it's just the solution of x to the power n equals to 1, and that is in the complex plane in this here. Now, if we put that nth root of unity there, it's a complex function, it's a function of k, so we get this new function of k, a of k. And notice, this is just the discrete Fourier transform. This is just the discrete Fourier transform of the signal 1, 3, and 2. And again, if you look here, this is just the discrete Fourier transform of our another signal 1, 2, 1. Now multiplying them gives us 1, 6, 9, 7, 2, which is actually the discrete Fourier transform of A convolution B, or C, what we have. So we calculated our C to be this 16972, and if we do a discrete Fourier transform, it will indeed be 16972 with the roots of unity squared here, and the power of 3 and power of 4. So you can see that using polynomial multiplicative properties, we can say that the discrete Fourier transform of two signals will equal to their discrete Fourier transform of the convolution. Hence, this is how we prove that discrete Fourier transform is actually the multiplication of two discrete Fourier transforms will be equal to the convolution of those signals. And this is not true for discrete Fourier transform only. This is also true for if we set x to e to the power minus st, which will correspond to the Laplace transform, or x to the z inverse, which will correspond to the z transform of the system, and so on. So, and another special case we have, if we set x to be this cosine vectors over here, these are vectors to be exact, then this will correspond to the discrete cosine transform of an image that we will use in signal processing, such as doing BJBG and stuff. So, in conclusion, convolution is something that we should be very much aware of, and the idea of convolution will extend to many places in signal processing. And thank you for your patience, and I hope you enjoyed this little demo.